So we've got 3 more speakers until the end of the conference for 2018. So first of all, I'm going to welcome to the stage Helena Simmonds of the Warwick Manufacturing Group. Helen graduated from Birmingham University with not 1 but 2 degrees in polymer science, and she began her career working at BAE Systems, where she got involved with the Typhoon aircraft, which is a pretty cool project, we can all agree. And since then, she's been working on a project recently which has been so successful it's actually won her won the team the best in class for the automotive category of the JEC conference this year in Paris. So without further ado, I welcome Helena to the stage.
Wow, thank you for that introduction. That was good. So as they said, I'm Helena. I'm going to talk about the class project. So just give you a quick overview of the project, a little bit about materials, of course, because it's this conference, design and optimization, and then further detail about the manufacturing and where we go from there. So first of all, the project. This was an Innovate UK project on the IDP11 call, 2 years, and it was led by Ford, partnered with Gestamp, ourselves, and of course GRM Consulting. This is the original component. It's called the tie blade knuckle, and it's part of the suspension system on a Ford Focus ST. The project aims were basically technical, financial, environmental, high volume, tackling everything in once. In 2 years, we're going to solve the world. And driven by reducing vehicle CO2 emissions. So if we think about the aims, were in 4 areas, and all these areas kind of pulled in different directions from what you wanted to do. So eventually we end up with a compromise. So one area is weight reduction. The original steel component was over 6 kilograms, and we wanted to get down to 3.15 kilograms, which would be a 49% saving. Secondly, it's cost. We understand there is going to be a cost increase with using composite materials, and the target set by Ford was $30 per vehicle. Thirdly, this was quite important to the consortium. We wanted it to not just be made out of hand-laid pre-preg. We wanted to show a step change in the technology by using some high-volume processes and kind of targeting a cycle time of under 5 minutes. This is very difficult, as you'll see during the project, but we believe that this is the way forward at WMG and our group especially. Believe this is the way forward to kind of make that change from niche carbon composites in sports vehicles, etc., into the mass market. And of course, the engineering requirements. So there were strength load cases, stiffness load cases, and it went through a design verification process. So moving on to the design. We started off with an SMC-only design. So SMC has traditionally been a glass fibre material. You might know it's fiberglass. It's used in cars to make the kind of interior parts, generally not structural. More innovative SMC materials that are currently on the market now are called carbon SMC. So they use carbon fibres. So they're more expensive, but less expensive than pre-pregs. But they have the ability to flow and meet quite complex geometry requirements that you can't always achieve with traditional pre-preg materials. And also, on top of this, they don't have any waste. So all the waste that you get out when you're cutting off a sheet, this time, because it moulds and flows, you can put any shape in and just fill your mould, and all you're trimming off is a bit of resin off the edge. However, we couldn't make it all from SMC because the stiffness requirements were too high. I think the first designs were coming out with thicknesses of around 30 millimetres, so this wasn't feasible. So the next step was we wanted to combine it with pre-preg. So pre-preg is your more traditional carbon fibre composites with continuous fibres which will take the load and meet the high stiffness to weight requirements. And we thought we can combine these two and come up with the answer. So this was our first go at pre-preg and SMC, and this is where GRM really helped with their optimization techniques about where we need to put this SMC. So the SMC is red and the pre-preg is green. So to meet the hard points of the package design, such as the anti-roll bar and the brake caliper, we had to create some clevises to attach to the rest of the vehicle, and that's generally where you can see these red areas. However, this first design, that's like a rear and a forward of the part, had SMC on both sides. So when we add in the design of manufacture requirements, we can't achieve this. You need to be moulding against a hard surface for the pre-preg for the green. So 2.2, this time all the clevises were put on the underside of this. And we've got this kind of ski slope transition of the pre-preg. However, that ski slope is too harsh. If you think about forming pre-preg materials, the draping, it's kind of like trying to drape a piece of paper. So you can't have these really harsh transformations because, well, they're either unmanufacturable or you get wrinkles. So pre-preg and SMC again, this transition was then reduced. And again, all the SMCs on one side. So we're nearly there, but we didn't meet the strength requirements. So we made it even more complex and even more hybrid. And we came up with pre-preg and SMC and steel. So the steel is this kind of honeycomb structure you can see in the middle. So you've got the pre-preg running the lengths to manage the stiffness. The SMC coming out to meet the clevises, that gets your geometry requirements. Both of those reduce the weight significantly, and then the steel increases the strength in that knuckle area where the SMC is a weaker material. Of course, there's challenges with combining steel with composites. And one of these was we saw delamination at the steel composite interface. This delamination, one of the reasons we thought was due to differences in thermal expansion. So we're moulding at 150 degrees C and then cooling down to room temperature. As they cool down, the composite doesn't shrink as much as the steel does, and you get delamination. One of the ways to reduce this was a honeycomb structure was introduced into the steel insert. This reduced the thermal mass as well as taking mass out of the component, increasing the light weighting. Secondly, the strength of this bond between these layers was under question. And when we did our first challenges on plaques that you can see there, our first tests on plaques that you can see, there was a significant drop in the interlaminar shear strength. So we looked at some coatings that we could put onto the steel to improve this. So using some coatings, the honeycomb structure to decrease the thermal mass, and the honeycomb structure as well to increase the surface area and kind of key in the bond, we overcame that. So while all that design work was going on with GRM Ford and Gestamp, we went on holiday to Detroit and made some parts in Ford USA. So we used this is kind of a generic geometry called the double dome. So we had a pre-preg skin and then filled it with SMC ribs. And the purpose of this moulding was to understand really what happens, firstly, when you combine these two materials in the moulding process, and secondly, what happens when you mould SMC out of plane. So we'd got the parts back and we got them under the microscope. And I'll have to use my laser here. So this is pre-preg and this is SMC. And you can see here that the pre-preg has kind of impinged or been drawn into the ribs. We weren't expecting this. This is it under the microscope. So the yellow line kind of follows the interface between the SMC and the pre-preg. This one was done by burn off, so we just burnt off most of the resin to kind of keep the structure intact and have a look. So forever the optimist, the pros of this pre-preg moving is that we can strengthen this interface by pulling some fibres into the Z direction almost, where generally you wouldn't have any fibres in the right orientation. The con, of course, is that you get a reduction in the mechanical properties where you'd originally place them. So moving on to manufacturing the actual parts. When the project was scoped and set out at the beginning, it was envisaged it would be SMC materials, compression moulded, so it would be this there. By adding in these other materials, we kind of really expanded the manufacturing process. But what we didn't expand was the budget or the time. So at WMG, we have an automated cutting machine. So we felt it's very important in this project when we were introducing this technology step change that we didn't just do everything by hand going up to it. We wanted to show that you could use automation in all the preceding manufacturing steps as well. So we cut by automation, apply cutter, simple. It was quite slow for us. We thought this was about 8 minutes per cycle. However, we were using off-the-shelf materials, so there was 19 plies within the part. In reality, what you'd do is you'd use a higher weight material and cut less plies, so you had to lay up less. So we think that can be overcome. And as well, the blank shape, we kind of picked a blank shape that worked at the beginning. We could improve that and improve the material width to kind of optimise your nesting of all your plies and reduce your wastage. So secondly is pick and place, so the layup of the materials. At WMG, we have the facility to do this by robotics. So the idea of using a robot, quite simple. Firstly, you decrease your time, and secondly, you make it a repeatable and accurate process. This was a challenge with the materials that we used because of the tackiness, so it was quite hard to be able to pick them up but let them go as well, exactly where you wanted to. And as well, they all have, like the backers on them. You've got to peel that off as well in the process. So we managed it, but not within the cycle time, I'd say, and that's areas of opportunity, and we have improved that on future projects. And then next is the preforming. So this preforming was definitely not in the scope at the beginning, but once we'd introduced that complex prepreg design, it was apparent we needed it. So we had to do the preforming, but on quite a low budget. So we designed this tool and manufactured it in-house at WMG. But what it does do is it trims the blank at the same time. So it comes down, forms the shape, and then this last movement there, that bit is the trimming of it. Sorry. Opportunities in this area, firstly, is to automate the process. Secondly, the complex shape, and we were using a 2D frame, just holding it there. But when it goes into forming, you suddenly get that ski slope. Trying to get a frame that more matches that shape. And then finally, using some preform simulation to optimise the blank shape. Sorry, excuse me a sec. So, manufacturing the compression mouldings, this was the big step that we knew we were going to be doing. So we managed to manufacture or compression mould the prepreg steel and SMC in a single process step. We used off-the-shelf materials from Mitsubishi Rayon. We moulded at 150 degrees with pressures up to 100 bars, and this is where we did achieve the under 5 minute cycle time. Within the mould, there were 6 pressure sensors and 3 heat flux sensors and 2 dielectric sensors, which allowed us to monitor the flow of the material and the cure of the material with real in life. And I can sit back and show you a video.
At a high level, the key aim of the project was to assess the reduction in vehicle weight and its impact on CO2, principally due to composite materials. To get the expertise of SMEs, of the universities, was an immense amount of benefit.
Ford was having the lead in the project. Of course, we picked a very complex part also, the shape of the glass knuckle, as we call it. It's very three-dimensional. There's many interfaces in the part. The team really had significant design challenges.
We had strength requirements, so it was strong in certain scenarios. We had stiffness requirements and also buckling requirements.
Stamp contributed in terms of design development and looking at the process and the part, trying to get into mass production. It was pure innovation and something completely different to what we've done in the past.
We joined the project to develop two of our software products, TruePly and OptiAssist, within the Abacus environment on a live programme with OEM involvement from Ford.
Gestamp had to think very cleverly how to design the tyre blade due to the multi-performance requirements. We ended up using a quasi-isotropic layout made from both biaxial and unidirectional materials. The layout was optimised to give strength where needed, yet allow lateral deflection for vehicle kinematics and compliance. The laminate topography was also optimised to give maximum strength to weight ratio in a very tight package space. However, the overall key to the design was using the long fibres where required and the short discontinuous fibres in the remaining structure.
For material selection, we worked with various different material suppliers. We moulded them in-house and then tested them in-house and presented the results to the partners to make a decision about which materials we took forward.
The technology that we would develop to manufacture the part, we thought we could redeploy over the vehicle to make a much bigger weight save.
So preforming was something which we didn't originally scope for. So we did the tool design and manufacture in-house and then the process development. We took it to a point where we've proved the feasibility and we can manufacture prototypes.
The equipment we use is very close to what would be used in industry.
We worked with the machining group here at WMG and used their skills and expertise. The fact that we've managed to successfully produce prototypes in such a short space of time has meant that it's been really satisfying to work on this project.
The next steps of this project are probably to look at cost reduction, minimise the waste or reuse the waste.
At the moment there's a whole industry working on getting the price of the base material of the fibres down to a price that can be really used for mass production. So we as Ford Research can't wait for these materials to be there and then start thinking what parts are we going to produce with those materials. So we have quite some research projects ongoing at the moment to really look what parts of the vehicle to make the most sense to produce out of carbon fiber or fiber reinforced composites.
So finally, just to let you know what we've been doing since then. So we followed on this work. It was apparent that the preforming needed examining. So we've taken that preforming work from quite a manual process, and now we have a semi-automatic process in a more automated press where it shuttles the material in after some infrared heating and uses grippers to hold it where we can tension it exactly how we want. And also we're going to mould some materials that are an epoxy prepreg as well as epoxy SMC, because the materials that we used in class were epoxy prepreg and vinyl ester SMC. We're looking at some future suspension projects, and also there's quite a lot of research that could be done within the simulation environment, so some robust SMC flow models for these complex shapes, as well as looking at the flow of SMC over prepreg and what that does to the fibres. So as mentioned at the start, This was a JEC award-winning project which we're very proud of, and I'm sure there's only a few more months that I can talk about it, so I will. And just to say thank you for inviting me to talk, and thank you for listening.